Good morning. This is your stats sensei, Mr. Spensey, and we're here to talk about hypothesis tests for one sample proportions. So first off, hypothesis test for one sample proportions is very similar to that of means. The concepts are the same, the formulas change slightly, but beyond that, it's almost the same thing. So first off, basic review on hypothesis tests. Remember, the purpose of a hypothesis test is to determine whether the data support the claim or not. We always begin with the assumption that the null is true. So we're always going to have a true null. We say it's equal. We believe it to be the case, and then we'll check to see if we gather strong evidence against the null to see if we retain the null or not. Please remember, we never prove it. We really don't even like this word except. Really, we just choose to retain the null because we could not find enough evidence against it. When do we know if we have enough evidence? When our p-value is small. All right. If our p-value is small enough, then we say we have enough evidence to reject the null in favor of the alternative. Note, we do not prove the alternative, we just reject the null. So we gather evidence. And we gather evidence by collecting a sample. If our sample has a p-value that's small enough, we reject the null. And so then once we collected the sample, we have to gauge the plausibility of the evidence. How likely are we to get this if the null was true by random chance? Because we know all samples vary. So by random chance, we could get a sample, and it's how likely are we to get it, okay? Please remember, we never have 100% certainty, but we still can quantify our belief using the p-value. All right, so when we get to our hypothesis, we state it like this: P1 or P equals P naught. P is the true population proportion, and P naught is the claimed population proportion, and that's going to be some number that we have as a decimal. Then, of course, our alternative can be expressed three ways, just like that for means. P does not equal P naught, which means we have a two-tailed test. All right. P is greater than P naught, which would be an upper tail test and shade like this. And remember, our P is going to be claimed here. All right. And then ultimately, we have a P is less than, which is a one tail, lower tail. Once again, the actual claim, the population P, the population parameters here, and then our sample P is down here. Now we note our sample P as P hat. Okay, please remember, p-value is in the tails for both of them. If it's smaller, for all of them, if it's smaller than alpha, we reject. And again, the definition, the probability that we'd find a test statistic as extreme or more extreme given the null is true. And we decide based on the situation and the threshold alpha we determine prior to running the test. So they'll either choose it for us. If they don't choose it for us, we'll set alpha equal to 0.05 just to be consistent. Our formula is p hat minus p naught divided by the square root of p naught, q naught, and n. So first off, let's talk about this. We had before, when we were working with the t, we would say that it was x bar minus mu s divided by the square root of n. Well, x bar is now p hat. This was our sample mean. This is our sample proportion. This is our claimed population mean. This is our claimed population proportion. And this is that right here was known as our standard error. And this is also our standard error. And one thing I need to talk about is Q. And as we've said before, Q is just equal to 1 minus P. And if we're going to use Q, you need to always define it, okay? All right. Also, we always will be running when we're working with proportions, this is nice, all proportions will always be a z-test. And the reason is we believe P naught is true. We believe it to be true when we start, so we have to use what we started with. And since we believe this is true, this is the population proportion. And because we believe that it's true, then, and that makes up our standard error, we have to say, you know what, this is going to be a z-test. Because remember, with a z-test, we know the standard deviation of the population. Well, here we're claiming that we do. All right. I put a little star and just note that for yourself. So we're going to go ahead and look at the recipe. And it starts off very much the same. We're going to write our null or an alternative and define the parameter and context. Those are the first two things. Which order you choose to do that depends on your personality, what makes is comfortable for you. The null, P equals, and by the way, we really don't need the not. You can just write P equals. The alternative, P does not equal, or P is less than, or P is greater than. Our conditions. We start off with the same conditions as simple random sample. We also have the n is less than 10%, so that hasn't changed. But then this right here establishes our normality. We need to verify that our sample is large enough. All right, and our sample becomes large enough if NP is greater than or equal to 10 and NQ is greater than or equal to 10. Now, keep this in mind. When we were working with means, our N had to be greater than or equal to 30. That was the normality condition for central limit theorem. This is normality for proportions, okay? Both must be true. Can't be just one or the other, it has to be both, all right? We've already talked about our equation. We're gonna go to a different part of the calculator, but it's not gonna be a big deal. And, oh, you know what, I should say this, and I'll say this again when we get to the calculator. The number of successes must always be a whole number, but you'll see that when we get there. All right. We'll run the test, we'll get a p-value, and we'll say what the p-value is and compare it to alpha. And then our p-value is this, we reject the null. There is sufficient evidence that alpha equals 0.05 to suggest the true population proportion. So no longer true population mean, it's true population proportion, but you otherwise see this is exactly the same thing. So we're going to go ahead and look at a scenario. And a union spokesman claims that 75% of union members will support a strike. Well, this is the claim. So because this is the claim, we will believe it initially, and then we'll try to gather evidence to see if it's in fact false. A company negotiator believes the true percentage is lower. All right, this kind of gives me the inequality symbol of lower, and runs a hypothesis test at 10% significance level. So they're telling us this time that alpha, instead of being 0.05, is 0.10. What is in conclusion if 87 out of the simple random sample of the 125 union members say they will strike? Well, this is important. We will come back to this in a moment, but that's going to be very important information. So our null hypothesis, we believe their claim is 75%. The alternative, we're checking it to see if it's less than. Define our parameter. Let P equal the true population proportion of union members who will strike if demands are not met. Conditions. All right. Well, they told us a simple random sample, so they gave us a random sample. So this was given. That was nice of them. N is less than 10% of the population. Well, what was our N? N was 25. So 125 times 10 is 1,250. Reasonable to assume that there are at least 1,250 union members. All right. Then we need to check our normality. NP has to be greater than or equal to 10. Well, in this case, the number of people who once said that they would strike is 87. So NP was actually calculated for us. We did not have to calculate it by hand. They gave us the value of 87. So this is like the number of successes. So we basically had 87 successes, and then we have the number of failures, those who said that they weren't going to do it. So 125 minus 87 equals 38. All right. Well, both values are greater than 10, right? Since both are greater than 10, then the sample is large enough to use the normal approximation. Okay, so we're going to go ahead and plug this into the calculator, and we'll explain what this, actually, let's talk about p hat first off. P hat is the sample proportion. Well, our sample size was 125, and the number of successes was 87. Well, if that's p hat, then q hat would be 1 minus that, which is 0.304. So here we go. We're going to set this up. Stat, test, and we're going to drop down to number 5, which is 1 proportion z-test. Well, our claim was 0.75. We had 87 people who said they would strike. That's the number of successes. And then our population was size 125. And we had a less than symbol. And then we can go ahead and press calculate. And we end up getting a z statistic of negative 1.39. And if we were drawing a picture, we go, you know what? This was the claim here at 0.75, and we ended up getting 0.696. And it makes sense that this would be a negative z because z is centered at 0, and we are below the initial claim. So we would expect to have a negative z, so negative 1.39. And this area is 0.0816. Now, I didn't show my work. I didn't write down the formula. I need to go back and do that. Make sure you always do that. So p hat minus p, and then you can just put p 1 minus p over n. Well, p hat we calculated as 0.696. And remember, that's just the same as saying 87 over 125. Here was the initial claim. Now be careful here. Notice that this is the population, this is the actual claim, this is 1 minus the claim. These must always be done for the population claim if we're working with a hypothesis test. All right, for hypothesis test, this number here will always be here. You've got to use those values. And then once again, there's our z, our probability, and we had an alpha of 0.1, so we're going to reject the null. So our p-value is 0.0816. We reject the null. There is sufficient evidence at alpha equal 0.1 to suggest that the true population proportion of union members who will strike is less than 75%. We believe that less than 75% of the members will strike. We do not believe the union's claim. All right. Always important to actually answer the question. That's actually the question, but we also need to give our summary. All right, from now on, please make sure that we not only give the summary, but we make sure that we answer the question. We weren't picky on that before, but now that we've done a bunch of hypothesis tests and confidence intervals, we will be picky about that. All right, so explain the meaning of the p-value in the context and the type of error that may have been committed. Well, first off, definitionally, p-value is a probability we get a test statistic this extreme or more, you should say or more, given that the null is true. All right, well, that's the definition, and that gets you no points. But as one of my students so eloquently say, that's brown nosing, and brown nosing helps on the grading end because it lets the grader know that you know something about p-value. So in this case, there was an 8.16% chance, if you want to say there's a 0.08616 probability that we get a test statistic this extreme or more in favor the true proportion of union strikers being less than 75%. Where did this come from? What was our alternative? HA, less than 0.75, when in fact the null is true and HO, P equals 0.75. 75% of the union workers would strike. Okay, so that takes care of the p-value part of this. The next part is what type of error? Well, we rejected the null, So the only type of error that we could have committed was a type 1. A type 1 error is rejecting a true null. All right, so once again, I just definitionally said that, but then I need to talk about the consequence. In this case, even though they didn't ask for it, we should do that. In this case, committing a type 1 error means that we mistakenly believe that less than 75% of the union would strike, when in fact, the 75% of the union will strike. The consequence is that we will give it bad advice to those negotiating a labor deal. In other words, we believe less than 75% will strike, so we don't think it's as serious a problem as it actually is. All right, and that can negatively impact our labor negotiations. Thanks for watching. This is your Stats Sensei. In the next video, we will be introducing confidence intervals using the same one sample proportions in the same scenario. I look forward to seeing you then.